It's really a great privilege for me to introduce Mark Uhran. He came to us appointed by ORNL as our point of contact back when they were highly suspicious of our efforts, I'd say along about April or March. And I didn't know anything about him, but what I've learned since is that not only is he a great guy and somebody you really want to know well and have on your side, but his history is fantastic. He went to NASA headquarters, what year? 1990. And wound up being the man who got the space station built, the International Space Station. He presided in the trenches for a few years and then was appointed to head the whole thing. And the last, 8 years, 7 years, you were completely in charge of it. So the reason that it's up there orbiting now is because of Mark and his skill in managing the whole thing. And I know that now he's going to probably tell us about where we go from here, but the country owes him great thanks for a really monumental effort. Mark Uhran.
Thank you, John. That was far too generous. I was actually more a learner than a leader during my tenure with NASA. I spent 28 years with them. But I was fortunate enough to come in right at the very beginning of the International Space Station program in 1984 and watch leaders from principally the shuttle era, but there were also a fair number of Apollo folks that remained with NASA at that time. And these were the people that really led the design, the development, and the on-orbit assembly of the space station. I, by virtue of the fact of having spent 28 years there, you can't help but rise to the top. And by the time I was spent most of that period as an advocate for how the space station was going to be utilized, the mission objectives of the space station, which is I'm going to talk a little bit about here. But then, full disclosure, I chose in 2012 to leave the space business. Working on the ISS for that many years was like running at a full sprint every day. And it was tiring. I decided that I wanted to do something easier. So I came down here to ORNL and joined the ITER project. Which has been great fun, and it's another international consortium. For those of you that aren't familiar with it, it's a consortium to build a 500 megawatt hydrogen fusion reactor in southern France. And many of the same team members that build station are on the ITER global team, but very few of the same people. It's a very different organization and a little bit of a different management model. So I want to blend both what I learned at NASA working space station and trying to keep it sold, which was one of the principal challenges for all those years, with what I've learned more recently on the ITER project, and put this all into a set of about 7 major points that I think are necessary to enable the future of human spaceflight. So with that, let me go ahead and begin. This particular illustration, I put this together kind of at the last minute last weekend when we found that there was going to be a gap in the agenda this morning. And I grabbed this picture because I always liked this photo. But I realized when I was reviewing it that this must be some kind of graphic composite. This is not an actual photograph. And you have to really look closely and know a little bit about space to realize where the clue is. But this astronaut has no tether. That would never have happened on the International Space Station. And I don't think there's one conveniently hidden. But nonetheless, I like the Photoshop version, and I'll probably use it again in the future at some point. A couple words about the ISS. 500 metric tons, 6 crew, inhabited by these crews for about a decade now. Incredibly multi-purpose. I mean, that was both the advantage and the disadvantage of the International Space Station. When we began in the 1980s, the Langley Research Center had established what they called a mission requirements database. And this had some 400 or 500 different potential uses of the space station. And I recall studying that database really closely because that was what my interest was in, what we were going to do with it. And there were over 250 TDMX, or technology development missions. 250. And that was at the beginning. Of course, during the lifetime of the program, there were probably at least another 250 identified. But when you think about it, and you think about government budgets, there was no way that we were actually going to get the opportunity to demonstrate that many technologies. And that's what was that was really the most important mission, was being able to field and demonstrate and advance new technologies up to the readiness levels that would be necessary in order to move humankind out of low Earth orbit. Because throughout the history of the space station program, which was probably the most intense period of the shuttle program, because the shuttle was what was used to build the space station, NASA knew they didn't want to stay in low Earth orbit. Ever since the Apollo mission, NASA clearly knew that they wanted to go the next step and not remain in low Earth orbit, but we got kind of stuck in low Earth orbit with the space station. In the long run, it was probably a very good thing, and I'm going to get into the reasons why for that. But with a mission database that had some 500 or 600 different aspirations of scientists, engineers, and entrepreneurs, we had to figure out how to design a vehicle that could accommodate 80% of that. And that's a long process I won't get into, which we actually succeeded at. But in the course of succeeding, I set up the critical parameters at the Critical Design Review in 1993 that ended up establishing what the crew size was going to be, what the volume was going to be, what the logistics, the transportation up mass and down mass was going to be, power, thermal, and so on and so forth. And of course, these were the parameters that drove the size of that 500 metric ton spacecraft. Well, there was no way of knowing back at Critical Design Review in 1993 that in 2008, NASA was going to get direction to put down the shuttle fleet following the Columbia accident. Well, the space station was designed completely to be serviced by the shuttle fleet. In fact, it was to take, a space shuttle will deliver about 20 metric tons to the space station orbit, and we planned on 4 to 5 flights per year, so 80 to 100 metric tons of resupply and return. When that capacity went away and was replaced by the fleet of rockets that we have today, both mostly commercial is what we're using today, and partner launch boosters, that fleet, although it comes from around the world, is almost like a fleet of pickup trucks. They have anywhere from 3 to about 5 metric ton capacity. So you had to launch 6 or more of these things to equal 1 shuttle flight. So that was all technically possible, and of course that's what we've done for the past 10 years since the assembly has been complete. But because that logistics was cut back so severely, many of the previously foreseen applications of the space station could not be supplied. And that was among the reasons that I left the space business. And I recall telling some of my colleagues at the time, NASA's not going anywhere with chemical engines. Call me if you start using nuclear propulsion in space. And so I am just thrilled 6 years later to see that the possibility is really palpable that we are going to see the development of nuclear propulsion in space. And that, I don't like to use the Washington, D.C. buzzwords about things like game-changing technologies, but boy, NTP is a game-changing technology, and it's going to change the entire future of human spaceflight, hopefully within my lifetime. Okay, I like to bring this slide up only because it was the theme of my last lecture at NASA just before I retired. This is Steve McLean. Steve was a Canadian astronaut who he and I had a rough and tumble time early in the program arguing about how to configure it for utilization, and became good friends by the end of it. And then he went on to lead the Canadian Space Agency as the director. I think he's moved on since then. But the real key to maintaining the forward motion and maintaining the budget necessary and the workforce necessary was the spirit of relentless pursuit. People just would not stand down, no matter what how severe the political opposition was. And I think that's going to be true in all spaceflight endeavors. Although there is public support for space station, it's not universal. And we live in a society where there are many competing priorities, and space has a difficult time remaining at the top, close enough to the top of that competition to get robust funding. So relentless pursuit in the spirit of Winston Churchill, never, never, never give up. And that's what it takes with the space station. That's what it's going to take with the technologies that we heard here in the past 2 days, a real spirit of relentless pursuit. But we also need a good dose, a subset of we've talked about the technologies for 2 days, which is what we should have done. But now we need to put the technologies on pause and ask ourselves, what do we really need in addition to the technology? Because these end up being the determinants. These are, in many cases, much more difficult to achieve than the technologies, although as scientists and technologists, our passion is with the technologies. And the first one was mentioned yesterday coming right out of the gate. You need a singular mission objective. The ISS started out, it had 8 mission objectives. There was a major downside at the end of the 1980s, and they were reduced to 4 mission objectives. And by the time the shuttle fleet was taken out of the equation, we were left with arguably 1 to 2 mission objectives. And there was not unanimity about what those objectives were, which was very damaging to the program. And there hasn't been unanimity about what NASA's mission and objective should be. And I want to tell you this morning, over my history at that agency, the most constraining factor to its forward motion was the disagreement over the mission objectives, over where they should go next. Now, most often you hear it's either the moon or Mars. And I think there's a way to take a step back from that, which I'm going to share with you here. And we've seen bits and pieces of it over the last couple days. In order to get from a singular mission objective to a paradigm. And I'll invoke the von Braun paradigm, which I still believe was brilliant leadership, and show how it relates to this paradigm that I'm going to propose today. We'll also talk a little bit about public support. I think we're at a period of time where some unusual events are intersecting that are going to allow space to go forward. The technology alliances were just critical, and I want to spend some time on that. What they do is they leverage your funding, and your funding is going to be necessarily constrained. I don't think we're going to see the kind of carte blanche national policy that we saw with Apollo or with Manhattan, because those two projects, when you really think about what drove them, it was the fear of fascism and the fear of communism. And those are big fears. And they drove a national policy in the energy program, and then later in the military program, and then later in the space program. Technology selection, doing technology selection is just a bear, because there is no shortage of good ideas. What there's a shortage of is funding for the good ideas and a process that selects those ideas, removing as much inherent bias as possible. And that's not easy to do. I believe that our NIAC program does a very good job of that. I got to say something about O&M costs, just because the last two major programs were the shuttle and the space station, and you all know what the operations and maintenance cost was on those two vehicles, those two programs. That learning experience has totally changed NASA's strategy going forward, and I want to make sure everybody is aware of that. And then finally, what I mean by exhaustive teamwork on design reference missions is we don't know the answers. There are a whole bunch of potential technologies at various TRL levels, how they fit together into mission plans. You can illustrate some of those today, but you can't predict what the efficiency or the effectiveness is going to be for those technologies. So having a single point mission plan today is a high risk approach. All right, so let's get into it. I got about 15 minutes to get through these. The mission objective. So when you take the mission objective and you extend it over time, so you have multi-phased mission objectives, I think we all are in pretty common agreement that interstellar human spaceflight and being able to expand the human civilization is the ultimate objective. We probably also are in pretty close agreement that establishing a human presence and an ability to work in low Earth orbit is done. The shuttle, the space station programs did that, and they moved us ahead as a result of that. But we don't need to stay in low Earth orbit, or at least the government doesn't need to stay in low Earth orbit. So now what comes in between? Well, this is where it starts to bear some similarity to the von Braun paradigm. Remember, von Braun's paradigm was heavy lift for cargo, reusable space transportation for crew, a orbital, a LEO space station, so you could learn to live and work in space, and then a lunar base so that you could learn to live and work on a foreign body. And once you went through those 4 steps, you would be prepared to make a mission to Mars. So a couple things came off the track. The paradigm is absolutely correct, but a couple things came off the track in execution. One of the provisions is, as you develop those technologies, you've got to sustain them, not throw them away. You've got to build upon your technology base. And NASA got caught in a position where, in order to start the next program, they had to take the prior program offline. So what do? We lost the Saturn V rocket. It amazes me to this day that the capacity of the Saturn V which went out of service in, what, 1972 or something, hasn't been matched since then. And I think we're about to see vehicles enter back into that class now. But we threw away the Saturn V, our first heavy lift vehicle. We threw away Skylab, our first space station. We ended up throwing away the space shuttle, our crew transfer vehicle to and from orbit. And then we went back and said, well, now we got to rebuild a heavy launch system. And we got the Orion SLS program. Well, we've got to rebuild our space station, and we got the ISS program. Well, if we had kept those capabilities in the first place, we wouldn't have had to make that investment a second time. And this also gives you the distinction between the Russian and the US program. The Russian program is very much built on stepwise increases in capacity. They don't throw anything away. And they don't design based on performance optimization so that you get the most expensive and the highest performance spacecraft. They design on the basis of reliability and upward compatibility in the architecture. So this was one of the benefits of the space station program. It allowed the Americans and the Russians to work together and start to respect each other's different approaches. So everybody knows we want to be able to get to Mars, and we need to be able to live and work productively there. And as von Braun's goal was actually interplanetary space flight, not just a human mission to Mars, where in situ resources were being developed in order to enable that interplanetary mission. But now the missing piece, and what I'm going to talk about a little bit later today, is rather than building another big infrastructure project, building a proving ground in space where the O&M cost is as low as possible, allowing NASA's flat budget to be diverted into technology development, which is where the real need is. And I think that's the path that NASA is on, or at least some of the current leaders are on. And I want to elaborate on that path in a little while. Okay, see if I can pick up the pace here. Public support. Public support means taxpayer dollars. These are government agencies. What we're seeing, I think, somebody correct me if I'm wrong, for the first time in 50 years, is interest, potentially collaborative interest, across both NASA, the Department of Energy, and the Department of Defense. Now, there's always been dialogue between those three agencies, but in terms of active collaboration and pooling of resources in order to develop new technologies, I think we're on the threshold of that. And I think nuclear thermal propulsion is the best example. They all have different missions. NASA has civil space exploration. DOE has nuclear power in space, and of course DOE has our national defense posture in space. I don't want to elaborate on the national defense posture, mostly because I don't have time, but there are other events going on in the world that may produce a forcing function similar to what we saw during Manhattan and Apollo, and we can talk about those afterwards. The technology alliances. The most important aspect of the alliances is that they leverage your money. They really leverage your money tremendously. I mean, it's like a doubling or a tripling or higher effect. We never would have built this space station without the launch systems of all those other partners. And in fact, after the Columbia accident, we wouldn't have been able to maintain the space station in a crewed capacity without the Russian partnership. Very expensive for us to maintain the Russian partnership. I won't get into the details on that, but you're probably aware of them. And we were able to develop our own commercial capacity at the same time. These alliances came in a lot of different flavors. It wasn't just the launch vehicles, but when you looked across the globe, the operations centers that were associated with that are still in operation across the ISS program are incredible. I mean, there's 10 to 20,000 people actively engaged every day in civil space across these operation centers. And that did not exist a generation ago. You'll certainly agree. Will it exist a generation from now? We want it to exist a generation from now, but we can't take it for granted. We have to work to maintain these alliances and expand these alliances. The alliances are incredibly important. Even a partner with a small stakehold, Canada had a 3% share in the ISS, but the robotics that came out of Canada are just awesome. And for those of you that aren't intimately familiar with the mobile transporter and the ISS remote manipulator system and the special purpose dexterous manipulator that is at the end of it, you put that system together and you have something like 26 degrees of freedom in those robotics. That's unheard of. That's like a piece of science fiction in and of itself. And they can be teleoperated from outside of Montreal, Canada, at a ground-based control station. So 3% partner made the difference, knockdown. Great people to work with, too. Systems engineering. I took systems engineering for granted. I learned it over 30 years at NASA and was impressed by it, and then was shocked when I left NASA to see the absence of it and to see how mature it really was at NASA. Systems engineering was initially developed by RAND to help the US Air Force in the 1950s develop the Intercontinental Ballistic Missile Program. So NASA, almost immediately upon its inception, began the Apollo program and decided to apply the RAND systems engineering principles. And of course, Apollo was a success. So NASA literally institutionalized systems engineering at all of its field centers. And you'll find SC&I directorates that maintain this absolutely critical capability. And one of the issues with systems engineering is how many people don't understand what it is. It's not just engineering a system. And systems engineering is being able to take a holistic view of every different discipline that's required to make a system work and evaluate every decision, because with these big complex programs, it's nothing but a decision mill. I mean, you're getting trade decisions several a day, and some of those trade decisions are in the tens or even hundreds of millions of dollars. The trade decision on whether or not how to operate the space station after the shuttle fleet was taken out of the equation was a multi-billion-dollar trade study. And I was able to both participate and watch the politics behind that. So being able to make decisions, taking all aspects into consideration in a collegial manner, where people, each of these disciplines respected the other disciplines. The guy that ran logistics, resupply to and from the proposed and then built spacecraft, was every bit as important as the guy that ran assembly of the spacecraft. They had equal stature in the decision-making process. And I don't know how you can build really complex infrastructures without that kind of systems engineering discipline. And when we talk about moving through that paradigm, that discipline is going to be required because there are going to be suppliers of various elements from all over the world, which means those elements have to meet and mate and operate successfully together for the first time in space. And that's a trick. That is not hard, not easy to do. NASA made this look easy on the space station program, and as I said, I just took it for granted until I left. All 4 degrees of freedom are constantly being exercised, and this is just an artist rendition of what it's like to have 4 degrees of freedom in space. There's a lot of different possible solutions. But the optimized solution, the most effective solution, and the most reliable and safe solution has to be reached through a joint effort. All right, I mentioned that technology selection is just a tough, tough game because there are so many great competing ideas. And this is a little bit of a feeble attempt to illustrate how biased we all can be and how important it is to try to get as much bias out of that equation as possible when you're doing technology selection and trading technology A, B, and C across each other. You can end up with a product that doesn't work at all, or a product that works but could have worked much better had there been a more objective selection process. I do want to say, because somebody made the comment yesterday, I think John did, about there not being a phase 3 NIAC. And so I went and I talked to Jason about that because I wanted to get clarification. That would clearly be a foul if there wasn't a phase 3 NIAC. But what I understand is in the current NIAC model, their success is determined if one of the other NASA directorates picks up the project and then funds it in a program. And that's how it gets picked up and run with. So I do think the NIAC model is very successful. And Jason could show you a series of examples where that has happened, which is encouraging. Okay, this is probably the key one. It's the simplest chart in the set, but it answers the question that's been debated for several decades now. What's next? Lunar base or mission to Mars? That's been the perennial debate at NASA. Now think about this. If NASA were to embark on a lunar base, what would it cost to operate and maintain that base? It would eat every element of funding for technology development. We might achieve some useful incremental gains by being able to have people on the moon permanently, but if it took our entire budget to keep them there healthy, that lunar base may be the wrong idea. And so I think what NASA has done is they've come to a middle ground that can accomplish the same kind of goals that von Braun had in his paradigm for a lunar base without running the risk of the O&M costs taking over the budget. I don't think I need to spend too much time on this because I've already alluded to it, and I'm just about done here. But it's just another illustration of how the decision-making is incredibly robust, and you can't underestimate it, and it has to be done properly. And then I wanted to throw in a quote from Mencken here at the bottom. For every complex problem, there's always an answer that is clear, simple, and wrong. And that's what you're trying to avoid. Okay, we're going to close. So pending before the White House right now is NASA's FY20 budget proposal. That proposal includes a new initiative called the Gateway. The space station is currently authorized to operate until about 2024. And although there is a debate about should we extend it again or should we commercialize it, and I'm not going to go into the details of that debate, I think it will be splashed shortly after 2024. And I think that's the right thing to do because we need to move on to the next phase. We need to free up that space station budget in order to be able to invest in broad-based technology. So what NASA has proposed is this gateway, and of course, very mixed reaction from the space community, which has always been the case in the past, because everybody's got a better idea.
Well, what this gateway really is, if you think it through, is it's a mobile dry dock in space. It's about 1/10 of the size of the space station. It's not permanently crewed. It's crew-tended, we call it, or crewed when it needs to be. And every single element, except for the new power and propulsion element, which is actually, I believe, probably going to end up being ion propulsion, because you don't need a whole lot of specific impulse to maintain this dry dock at a Lagrange point. All these other elements, the Orion is already built for all intents and purposes, and it's available. And of course, there'll be commercial crew vehicles available as well. But each of these other elements are existing designs that were deployed on the space station and provided by partners around the world that are also interested in providing them again for this dry dock. So what does this dry dock enable you to do? Well, first of all, it's a mobile dry dock. Since it's sitting at a Lagrange point, it can move between Lagrange points at very low energy cost and be the pit stop. I've been searching for, what is the right analogy to really help people understand this? And it's a lot like a NASCAR proving track with a pit stop. And this is the pit stop. No matter what kind of tech demo you're trying to do in space, the chance of you getting it 100% right on the first try are pretty slim. It's going to take some in-space development, and you don't want to have to go run all the way back down to the bottom of the gravity well to resupply yourself. You want to be able to have a series of these. So that's the Gateway project. My walk-off slide, I want to transition into this next session. I think most of you are probably familiar with the Interplanetary Transport Network. How many people are familiar with it? Not too many, actually. Well, for those of you that aren't familiar with it, I recommend you just go to your search engine and plug in Interplanetary Transport Network. And this is a mathematical theory of orbital dynamics that it comes out of JPL and several other orbital dynamicists at universities. Plenty of good information published on it. But what it says is you can move around the entire solar system with very little delta V, very little energy, very little requirement for propulsion if you just move from Lagrange point to Lagrange point. Now, there is an inevitable downside. It's extremely slow. So you're not going to be moving people through the Interplanetary Transit Network. But here's where I want you to put your science fiction imagination on as we move into the next session. And just imagine a future where the biggest, dumbest, heavy lift boosters, we'll call them Falcons, are being used to put 50 metric ton freighters and tankers into this system. And you're launching maybe 4 times a year, quarterly basis. And every tanker is full of either oxygen or hydrogen or nitrogen or food or some combination of that. And these are put out to drift into the Interplanetary Transit Network. And over a course of 10 years, these supply caches are now all out there. And at some point in the future, those same resources, instead of having to drag them up out of the gravity well with these big dumb boosters, you actually produce them in space, either through asteroid mining to resupply these cargo caches, or I can easily envision robotic gardens in space, because we see them, we already have them at Kennedy Space Center, or at least we did a while back. So here's a way to populate the entire planetary solar system with supplies over a period of a decade that can service missions on into the future. And those vehicles are all flagged United States and protected by a Space Force. Thank you very much.